On chip, actually, there are some interesting applications for op-amp. For example, I talked again and again about such kind of voltage driver instead of current driver. So what is the most important characteristics for such kind of voltage buffer? To get 100% of the input voltage, actually we hope the input resistance hopefully should be infinite. And hopefully we can drive all the output voltage to our load. So we hope RO should be 0. That is we discussed in last week. Yeah, so you can connect your op-amp, never mind how much gain it has. We can connect V into the non-inverting input, and we connect output back to the inverting input. That's it. With such kind of negative feedback, usually you can much stabilize the overall operation, and also that close to 100% of the input will be delivered to the load. That's it. So what's the closed loop output resistance? Yeah, I guess again you learned it already from microelectronics, but I told you again and again. Yeah, how much gain you sacrifice, right? For example, here, right? Yeah, if A beta is quite huge, then you can get the output resistance is reduced by such amount. Yeah, similar for input resistance. You can increase the input resistance for this. You can decrease the output resistance for that. But if this is not an op-amp, for example, that is some kind of current amplifier. Sorry. Okay, then I promise you, you can decrease the input resistance and increase the output resistance. What does it mean? What do you want? Almost all of them will be enhanced by such kind of negative feedback. Okay, and for such kind of voltage buffer, usually we design the gain around 100. The power consumption, microwatt, unity gain bandwidth, megahertz, blah, blah, blah. Anyway, for such kind of very easy buffer, usually they cannot drive heavy load. What do I mean? Heavy load means what? Why they cannot drive heavy load? Simply because the driving current is not so good. The so-called driving capability is not so high. Since the current is not so good, and it means you cannot drive large capacitance or small resistance. Don't think, it cannot drive large resistor. No. The larger the resistance, the easier to drive. Okay? Because for very large resistor, it only needs very small driving current. So don't get any kind of misunderstanding. All right? Since it cannot drive heavy load, it means what? For off-chip application, if you would like to drive the other out of your chip, it's a big business because your output need to connect to the I/O pad, then bonding wire, then the output load means a lot of parasitic capacitance. Okay, usually even for the pad itself, maybe around 3 to 5 picofarad. Usually it means huge or at least very large capacitance on chip. Okay, and how about the off-chip parasitics, the resistance, the capacitance? Wow, it means what? You need third stage to deliver very large output current. Otherwise, you cannot make it. But for on-chip application, that is the usual case. We only drive light load. Under such kind of condition, don't design the output current to be huge, because the more output current means what? Yeah, the more power, the more area you need to waste. It doesn't make any sense. All right? So for on-chip, we focus very much on light load, on low power. Yeah. And then, before we go further, hope I can help you even more, especially about the voltage operation range or operational voltage range. 电量操作范围. Anyway, for example, yeah. How about input common mode range? Yeah. What is the average input voltage? How large, how small they can operate with such kind of very simple, I mean single stage op-amp. Anyway, you can see that VIC need to be larger than 1 VT, 1 delta V plus the other delta V. So it needs to be larger than 1 VT plus 2 delta V, blah, blah, blah. Okay? Yeah. And also that it cannot be too high because this or that need to operate in saturation range, right? So at most, the input common mode voltage can be 1 VT higher than your V out. That's it. Okay? So if you move here over there, yeah, you can move over there, right? I can be 1 VT and delta V higher than V out. That's it. Okay? That is the maximum. So I need to be less than or equal to. That's it. Okay. Anyway, you can list all those equations, and then according to larger than or smaller than, you can have the direction, right? I think you learned it from not calculus, but far earlier than that. Maybe from your senior high mathematics. Anyway, yeah, just do it. Then you need to fit all those equations. Okay? Yeah. So how to fit all those equations? It means the union. Oh, no. How can I say? The overlapped area, 交集. Okay? So you need to be here or W then, smaller than, smaller than. Okay, where is the overlap area? In the middle. Okay, oh, finally. The shaded area is the operational ranges, not only for input but also for output. Okay? 斜线的区域就是输出输入可以操作的区域。Anyway, you can see that for the horizontal one, that is the input common mode range. So for the vertical one, that is for output. And what you can see is the higher VIC, it means what? The smaller output operational range, right? Or the smaller output swing. So keep this in mind, swing, very important terminology for our analog IC design. All right? So you need to think about it. Yeah. Where to locate your input common mode range. That is also very important according to your application during your design. Okay? Anyway, I am not recommending you, under such kind of circumstances, you need to design your VIC, the input common mode range, as smaller as possible. That is our hope, but you are not the one to make the decision. It is decided by your application. Okay? Got it? Because, hey, I would like to design my VIC here. Oh, then I can get such kind of very wide option. Forget about it. The application decides all the conditions. Okay? But if there's any flexibility, because you are the designer, yeah, you can try. You can try. But you cannot hope. You can always make it. Okay? All right, for such kind of single stage high-gain op-amp, some kind of recall, What is voltage gain? Don't forget, that is GM by RO, or GM over GO. Okay? Don't forget. This is the most important idea you need to know about amplifier. Okay? And then, yeah, according to, if you would like to increase the gain, then you need to reduce GO. Yeah, I mean output conductance, or increase the output resistance. Yeah. Anyway, anyhow, how do you make it? For such kind of, never mind that op-amp is simple or complicated. According to our systematic design, you only need to concentrate on quarter circuit. That's it. Okay? So, how to enhance the gain? I mean, from differential amplifier, because the quarter circuit is only common source amplifier. With such kind of common source amplifier, actually, the RO is not good enough. And how to enhance your output resistance? The easiest way is cascade. All right. So let's modify our quarter circuit from common source amplifier to such kind of cascade common source amplifier. Yeah. In this way, we can enhance the output resistance by almost 2 orders. But this is only the quarter circuit. You need to flip it to become the counterpart circuit. Then you have the left half circuit. Flip to the right to get the other half circuit. And apply your bias current, usually, okay, in the middle of the symmetry. That's it. Yeah. And how about the amplification, the gain? Okay. That is very simple, right? Because who convert the input current to output, the input voltage to output gain? GM1, right? And then by RO, you see from here to there, right? So what is that? What is the output resistance? By then that is GM2 and RO2 and RO1. Okay, that's it. Yeah, all of them. Then you will get the output gain. Just do it by yourself. Okay. If you consider the output load, then what is output? What is the output resistance? That is the sum of your output conductance, the replica, the reverse of your overall output resistance. Yeah. So output conductance. So what is output conductance here? Yeah, HCl, right? And what is the output conductance over there? Just reverse the how, blah blah blah. So you can get this one. Okay. Anyway, anyhow, that's it. Yeah. Never mind the design parameters, because I told you that is only good for optimization, automatic optimization, but usually you don't have the chance. Okay, you need to do it manually. I mean by your hands. All right. Anyway, I told you already. If you would like to enhance RO, then the bandwidth will be reduced. So no gain in gain bandwidth product. I warn you again and again. Yeah. That is only one. If you would like to enhance gain bandwidth product, yeah, you need to focus on this. But it is rather, it is comparatively much more expensive than here. Okay. Yeah. To enlarge this one for the gain, or by applying cascade for the gain. Yeah, this one is much inexpensive, much cheap. I mean. Okay, this is the quarter circuit. Then, as I told you already, quarter circuit, counterpart circuit. Then you have the left half circuit, flip to the right. Yeah, the other half overall circuit, and apply the bias current here. That's it. And what this? Now I show you the birth of telescopic cascode op-amp. That's it. Okay. In last week, I showed you the birth of differential amplifier, almost the most important building block for analog IC design, right? But the gain is not so good. To enhance the gain, now I show you, how to create such kind of very high gain op-amp, telescopic cascode. Nothing is impossible. All the op-amps you learned or you never learned can be created in such a systematic way. Okay, but again, you need common mode feedback circuit. Where to apply your CMFV? Where to apply? Where to apply? Always to the other side of your input. Okay, so your input here, you need to apply there to the other side. Okay, because this one is fixed from your design. After fabrication, if there's something wrong, you need to fine tune this. To balance the power of here, right? To make what? V out plus V out minus the average voltage in the middle of your power trails. Okay, just like the rails, the trails for the train. Sorry, 像铁轨一样. We call it. I think I mentioned already. Power rail. Okay. That's it. In the middle, you can get hopefully the maximum output swing. All right. Let's go further. That is for single-ended operation. Why you only get 50%? Or simply because we apply our differential input here. So for each side, you only get 50% of the input voltage. That is the reason why divided by 2. Okay. And for all the others, just do it by yourself. Don't bother me. Piece of cake. Very, very simple. Very easy. Okay. How do I estimate? For example, if you apply your input here, right? You convert the input voltage into output current, right? And output current here by overall output resistance. It is the out here, out there in parallel. So conductance will be easier for you. The conductance is summed. Then the reverse of your output conductance, the summation, right, will be your output resistance. That's it. If you hate such kind of common mode feedback circuit, then again you can apply diode connection to generate the bias automatically, right? You run it again and again, right? But in such kind of simplest configuration, the operation range will be limited. Okay? Anyway, how to estimate? From here to there, 1 VT plus 1 delta V, right? And again, the other VT plus the other delta V. So right now, from VDD minus 2 VP minus 2 delta V. Okay? So how about the maximum voltage here? According to PMOS, it can be 1 VT higher. For MOS, it can be 1 VT lower for the drain voltage. Okay? Okay? And then, how about the minimum for your output? Delta V, delta V, delta V. 3 delta V, that's it. Okay? Got it. You don't need to calculate. You just learn the power of estimation. Then you will roughly understand how wide your output swing will be. Okay? If you're unhappy, you say, hey, it is too small. As you like. Right? Yeah, you can see VDD minus 1 VT 2 delta V. That is what I told you for the maximum output. Okay? And how about the minimum output? 3 delta V. Delta V, delta V, delta V, right? 1 and 2, 3. That's it. I don't care. What's VDSS as who's MC, M9, M2, M4? I don't care. I don't mind because it doesn't deviate too much. Okay, there is no much difference. 2 to 300 millivolts usually. And how about VT? 5 to 6 or 7 hundreds of millivolts. That's it. Okay. Anyway, this is what I told you. Yeah, the option is VDD because here VDD there is ground minus 1 VT minus 5 delta V. Okay, so you can guess. Oh, all right, this is 0.5 and that's 0.2. Wow, totally VDD minus 1.5. But how much is your VDD? For 0.18, only 1.8. Wow, you have only 300 millivolts. That is not the exact figure, exact number, but you will know how much the impact with such kind of telescopic op-amp configuration. Okay, yeah, maybe you can try your very best to make it a little bit larger than 300 millivolts. But how large? Not too much. Okay, that is again the ugly truth. If you have no such kind of idea for the junior designers or students, they usually think, wow, with such kind of high-gain amplifier, oh, what is the output swing? Even it is not full range, 1.8. Maybe most of them will guess, at least 1 volt, or the smallest, the minimum, 50%. No, sorry for that. Sorry for that. Even less than 1/4, okay, or 1/5. Very, very small. But again, I need to warn you. Right now, for the so-called operation range, we are talking about the range for maximum performance, to get best performance. Okay? If beyond that, what will go wrong? The gain will be decreased substantially. That's it. But you cannot say, hey, beyond such kind of range, the op-amp will become malfunctional. 错误动作. No, it never. I mean, within the range, it can deliver you the best performance, the highest gain. But beyond that, yeah, the more you go beyond, the more degradation for your gain. 你超出范围越多，你的 gain 会变得越少，但是不会不动作。Okay? Keep this in mind. So how good your design will be, again, it's up to you and your application. That's it. If you are not happy, you say, hey, this is too small. Okay, what you can do? What is the first skill I told you already to enlarge such kind of output swing? What you can do? High swing case code. Okay? High swing case code. Later I will show you. It means ho ho, ho ho. Not here, right? It will be connected to there. Okay? And you need to generate. Nothing is free. You need to generate another bias here. Okay? That's it. Yeah, later I will show you. And how much you can gain. To my memory, only 1 delta V. Not much. Okay, but 1 delta V means maybe again 2 to 3 hundreds of millivolts. Not so bad. Okay, yeah, it almost double the output string, right? Anyway, before leaving, again, for such kind of telescope op-amp, I mean very high-end op-amp, if you apply this for output buffer, I mean voltage buffer, okay, what will be the consequence? To be voltage buffer, you need to connect your output back to your output here, right? Back to your negative input. Okay? In such a way, you need to be very, very careful. Here, with such kind of unity gain connection. Okay? Where? Wow. Oh, that's too far away. See, your output needs to be connected back to the inverting input instead of the positive input. Okay? So let's go further. Yeah. After such kind of voltage buffer connection, unity gain connection, you will put a serious constraint for the bias voltage here. Okay? All right, let's go for it. You can see, again, what is the, if you know VB here, right? With such kind of connection. Right now, V out equals V in 2. Okay? So what is the minimum voltage for V out? No smaller than 1 VT. Okay? From here. Right? So, yeah, V out minimum is VB minus 1 VT. Okay? And then what is the maximum? Because it is connected here, you cannot push it too hard to make this or that out of saturation. To keep both transistors in saturation. So you can see you need to be from here, right? 1 VT, 1 delta V here, right? And then you can be 1 VT higher, another VT higher. Okay, that's it. So you can see what is the maximum. Yeah, VB minus VGS4, it means minus 1 VT, 1 delta V. Then you can plus another VT. So yeah, for rough estimation, I don't care who's VT. I don't care about the body effect. No, that is too complicated. Okay? Then, so, it means what? The minimum is the same VB minus 1 VT. And the maximum is the same VB minus 1 delta V. So what is the difference? VT minus delta V. Right? So, even smaller than before. Okay? That is the difference between your VT and your delta V. How much you can get? 200 millivolts, I think. Yeah, is large enough for such kind of situation. Okay? Sometimes even smaller than this. Wow. For 0.18 micron process, 1.8 volt supply voltage, the best operation range for your voltage buffer is only, only 1/6. That's really sad. So lesson 1. Why I told you for voltage buffer, usually the gain is not so high. 100, good enough. Why? Because the higher gain means the smaller operation range for the best performance. Okay? Got it? Nothing is free. You need to pay for it. 如果当电压缓冲器 你的增益设计的越高，它最佳的操作范围就会大幅的缩减。所以我们通常不干这种蠢事。Usually, we don't design a very high gain for such kind of voltage buffer. Okay, medium gain, good enough. I mean 100. But with this one stage, I think it can provide you three orders in gain. Okay? Yeah, don't try. Anyway, if you think the output swing is not good enough, then we can apply again high swing cascade. All right, I show you already. But the expense is you need the other bias voltage, not only here but also there. Okay? And then how much you can get? Roughly speaking, because it is symmetrical to the left, to the right? So how much voltage here? VDD minus 1 VT 1 delta V, right? Similar for that. That's it. Okay, and you still, that is for the maximum. But do you modify anything here? I mean, compare this new circuit. Yeah, just use your eyes as cameras. Take a screenshot. 拍张照片，用眼睛拍照片 then go back to the original one. You can see, we only modify the upper part, but nothing is changed for the lower part, right? So, yeah, we only change the upper bound for UV out, but nothing happened for the lower bound. So you still have 3 delta V. That's it. So the maximum is VDD minus delta V, minus VT minus delta V. Previously, minus 2 delta V. Okay, that is the difference. Okay, so right now, but for the minimum, you have 3 delta V. So right now, the output swing becomes VDD minus VT minus 4 delta V instead of 5. So with such kind of high swing cascade, yeah, the benefit is 1 delta V more for your upper range. Okay, but what is the price? Not only one extra bias, it's harder to design, right? But also that, I promise you, the gain will be decreased. Not so much. Yeah, but anyway, keep this in mind. Again, nothing is free. For regular cascade and high swing cascade, okay? Whoa. With the same structure, with the same W over blah, blah, blah. I promise you. What's high swing cascade always, not usually, no, always provide you gain. Okay? The output gain will be reduced a little bit. Why? If you calculate, you will figure out the output resistance of high swing cascade will be reduced from regular cascade. Okay, that is the reason why. Nothing changed for GM. Okay, but RO will be reduced a little bit for high swing cascade. That is the background. Common sense for analog IC designer. Okay, nothing is free. Yeah, okay. Maybe you will be curious why I talk about voltage buffer again and again. For example, this is something we call switched capacitor integrator. Switched SC 切换电容 switched capacitor. Okay, for any kind of SC, especially for integration, you usually you always need to reset the overall circuit. Why? According to VOS. Okay. Nothing is perfect. Every amplifier has such kind of input offset voltage. But what is the consequence for VOS on integration? Since VOS is the DC term, after fabrication, it is DC, right? So it will cause a DC flow. I don't care the direction because VOS is positive or negative. Yeah, both with 50%. So the DC current caused by DC input offset will in this way or in that way. But anyway, you can see the voltage of the capacitor will be saturated. For example, if the current flow in this direction, then the output voltage will be pushed higher, higher, and higher, right? Finally, reach at most VDD. That's it, no more, right? After saturation, it will become malfunctional. So you need to make sure nothing will be saturated. But how? Reset. Okay? For the beginning of each operation cycle, you need to reset your switch capacitor circuit. During reset, only reset. Oh, simple to test. Some switch, usually MOSFET, transmission gate, more exactly. What is transmission gate? One PMOS and one NMOS connected in parallel, right? Anyway, yeah. For such kind of analog switch, it needs to be connected in parallel with your capacitor. During reset, you can see it is closed. It means your V out is connected directly to your negative input. Under such kind of circumstances, it looks like a voltage buffer. Okay? Yeah, and again, how to provide the best performance? You need to make sure every transistor for the op amp needs to be in saturation region, right? And again, you need to be limited by this one, okay? Unity gain buffer, this one. Please try to remember during the estimation, right? I mean for unity gain buffer, we didn't touch here or there, no. We focus this node, VB, and that node. Okay, so never mind, you apply high swing cascade or not, you still have the same unity gain buffer. I mean for output swing. The output swing is really, really limited. I mean for the best performance. Okay, keep this in mind. Right now, we talk about telescopic cascade op amp. If you think the gain is still not high enough, 1,000, you are not happy. You would like to push it further for 10,000, 100,000. Okay, let's go further. What you can do? Again, focus on quarter. Right? And I told you already. For a single transistor, if the output resistance, if the gain is no good, you need to enhance its output resistance, usually by cascade, right? But don't apply the other cascade. If you apply the second cascade, double cascade, sorry for that. I promise you, 0 volt for your operation range. It cannot work. It cannot be functional. I mean for the best performance. It cannot performance. It means the gain will be decreased. Then you simply waste your effort, your chip area, your money, right? So usually we don't apply, even though it is possible for MOSFET, but usually we don't apply any kind of double cascading. If single cascade is no good, then we can use such kind of gain boosting. Again, apply negative feedback to the cascade transistor. But never mind how large the gain is. Okay? as you know, this is only current buffer. What does it mean? The input current for M2 will be, if nothing wrong, will be 100% delivered to the output. That's it. So AI will be exactly 1. So never mind how much gain you have. All the gain will be sacrificed because AI is only 1. Right? Since you sacrifice all the gain, so what is the slogan? How much you sacrifice for the gain during such kind of negative feedback, you will enhance all the others by the same amount. OK? OK? 各讲一遍哈。负反馈最重要的口号是什么？你牺牲多少争议，你就会改善其他所有的参数，呀，等比率改善。OK？ 争议牺牲100倍，所有的参数都会被提升100倍。Anyway, that is what I'm talking about. All the gain will be sacrificed. So, what will be the consequence? For example, the output resistance will be increased by because the gain is sacrificed to 1. All the gain is sacrificed. Okay, so all the parameters will be enhanced by the same amount. I mean by A1. Never mind output resistance or output gain, because output gain is GM by RO, right? It is increased by A1. Then similarly, so what is the output gain? That is original telescopic case code, okay? And we enhance it by A1, that's it. If you don't believe it, okay, no worries, just derive it. How to derive it? You apply the small signal model, blah, 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 and I promise you. Yeah, that is, during deviation, you will get this. Okay, because A1, they are really large, so 1 can be neglected. Okay, so finally, you get this. Okay, believe it or not, by estimation, the difference between estimation and calculation or derivation is only 1 here. That's it, no more. All right, so I myself am happy, much happy with estimation instead of derivation because it's too time wasting. And only 1 out of maybe, 10,000, right? 1 out of 10,000, nothing at all. Again, the gain, the output resistance, blah, 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 will be enhanced by A1. Okay, that's it. And you can see, humankind created such kind of very high gain single stage amplifier. Almost 40 years ago. Your grandma studied such kind of op-amp structure. Anyway, in the past, I mean. Okay. But again, this is only 1/4, right? You get for full circuit. Anyway, I will show you. Wow. Okay, 1/4. Then you will have circuit, the counterpart circuit, left circuit, right circuit, apply bias current in the middle. Okay, let's go back. You may be curious how to make it. Yeah. Does it need to be another op-amp? Don't forget, this is only 1/4 of the very high gain op-amp. Okay? But even for such kind of 1/4 circuit of your op-amp, do you need another op-amp? Sometimes yes. But usually, that is too painful, right? To create this op-amp, we need the help of the other op-amp. And how about the other op-amp? We need the help of the other op-amp. That is too complicated. If you wouldn't like to apply one op-amp for the other, right? Then maybe this one should be good enough. Low gain amplifier, yeah, for such kind of gain boosting. And what's this? Again, common source amplifier. That's it. And how much is the gain? One order, I guess. Yeah, tens in gain. Okay, that's it. If you want to make it to be 2 orders, then usually you need the help of, I cannot say the other open, but at least differential amplifier. Okay? Wow. Wow. This is really complicated. But for very high gain, you need to pay for it. Okay. And for this one, yeah. Again, what is the operation range? From here to there, 1 VT, 1 delta V, right? And then the other delta V. So the minimum is 1 VT plus 2 delta V. Yeah, just estimate it by yourself. Okay? And this one is some kind of current mirror to be applied to this one. Okay, forget about it. Yeah. As you like. As you like. I don't care. Then you need to pay much attention to such kind of very, very high gain op-amp design. If there's anything wrong, you need to be very careful. The op-amp will become malfunctional. Okay? It means it doesn't work at all. You need to be very careful. Why? Because for such kind of gain amplifier, again, it has some kind of input offset voltage. Okay? If there's nothing wrong, I told you again and again, VOS, 50% is positive, 50% is negative. Okay? If it is negative, then according to the amplification, you will get, I mean, for your normal value, for the Q points, quiescent point analysis, H-spice will tell you, oh, how much voltage here and how much voltage there. Oh, but H-spice has no idea about VOS. Okay? So the real voltage here should be the original one plus A1 VOS. Okay? If this term A1 VOS is negative, you need to be very careful. For example, 2 millivolt here, right? A1. Okay, 100. Then you will have extra minus 2 millivolts here for the DC bias. Okay? Or if you are unlucky, 5 minutes or even 10 minutes, wow, I promise you, M2 will be cut off. That is the risk. Okay? You need to pay much attention to such kind of process variation. After fabrication, 50%, if nothing wrong, okay, if you do a good enough job for your design, for your layout, then 50% of the VOS will become negative. Then, more likely, 50% of the M2 will be cut off. Okay? Yeah. That's it. Because you need to have VT, 1 VT plus 1 delta V to make M2 survive. Alright? Then, for such kind of A1 VOS, more likely it will not only cancel delta V, but also, yeah, even make the voltage less than 1 VT. Okay? So, yeah, roughly speaking, maybe 50% of the fabrication process variation will make M2 cut off. Then it doesn't work at all. So how to prevent such kind of very bad situation? you need to make sure for such kind of variation, for such kind of structure, you need to make sure VOS never less than arrow. But how? How can you make sure your input offset voltage is positive? How can you make such kind of issue be positive? Okay, please think. What is the reasons? What is the causes of VOS? Huh? Remember? What is the main reasons? Why your amplifier, your op-amp have such kind of VOS? Simply because their left and right are not symmetrical. Right? Got it? So, how to, under such kind of circumstances, if you would like to make it positive? Simply make this one, the left and the right, not the same. Okay? What I'm talking about, you can make the W over L, especially for the differential input pair. For this one, the left or the right needs to be larger than the other side. Okay, got it? That is the cause for VOS, but also the cure for this problem. 大家听好不 ？VOS 的起因是一个坏事，但是它也是目前这个电路的治疗方法。药食同源啊。Okay, so that is another lesson you need to know. Don't skip, don't forget all any kind of bad issues. You cannot only focus on good issues. No, you need to focus on both, the good and the bad. Here, you will see the bad in the past right now is the cure, is the solution for the problem here. But you need to know the bad in the past. Okay? So, remind yourself, especially for new designers in the past, they only focus on good. How to make good performance. Yeah, but they try to skip. They try to forget the bad of the circuit. No, you need to learn both. Okay? A very good reminder for yourself. See? If this one is not good for you, I mean, again, if it is not large enough, then, sorry for that, you need to go over. The next step is differential amplifier. Okay? But luckily enough, because you need to apply such kind of gain boosting, not only for the quarter circuit, not only for the left, but also for the right. Got it? So, usually for such kind of differential amplifier, we would like to make it fully differential. I mean, one output for left quarter, the other output, okay, the other output for right quarter or right half. Make it? So, no diode connection. No, usually not. And this is what I would like to tell you. Moments ago, I show you. This is fully differential. Right? So, one for left half, and the other output for right half. That's it. Bingo. But this is only, sorry, I need to say, one quarter, the other quarter, and don't forget, they have counterpart circuit to the top. Okay? So, later I will show you this. Okay, yeah, that is the final structure. One quarter, two quarter, and this fully differential to drive both. And then, counterpart circuit. And we apply high shrink code. All right. Wow. I promise the gain can be as high as 100,000. Okay? But you need to pay for it. What is the price? It's really, really hard to design. Usually, for the first simulation, you will see, cutoff, trial region. It is really hard to make all the transistors in saturation region. Okay, you need to face the challenge. Okay, and even though you make it finally, you still need to pay for very, very high power consumption. Okay? Anyway, I teach you everything, but usually I don't recommend you to go for this. Don't design this because it's too hard to design and the price is too high for you to pay. Okay, the power consumption, the chip area, it doesn't deserve. Only when necessary. Don't be so brave. I would like to be the guy to design the highest gain in the class, in the company. No, you will kill your own future because that is too dangerous, too painful. Okay, too much price. You need to pay for it. Maybe even your future, you need to pay for it. Okay, don't be too aggressive. Ambitious is good, but don't like Chinese, too aggressive. Okay, 侵略性啊，侵略性。跟有雄图大略是不一样的。Okay, we can have a break here. Later I will tell you how to maximize the operation range. Okay, later. Yeah, after I get my coffee.